if anybody is still on the fence about whether global warming is related to human activity, then they should read the IPCC's fifth assessment report, which came out in 2014. Now, we're 7 years removed from that, so it's only gotten worse, as you'll see later on in this chapter. Okay, what is the IPCC? It's the Intergovernmental Panel on Climate Change, and it was a group that was organized by the United Nations in 1988. And their task was to review all the literature, the research that's been done related to climate change, and then to give an assessment to policymakers on what the risks would be and what some of the remedial action could maybe be. So they've been doing these reports since 1992, and they were always a little bit wishy-washy, especially the first three. They didn't ever come right out and say, yes, this is related to the warming that we're seeing is related to human activity. This time they didn't equivocate whatsoever. First of all, the warming of the ocean and the atmosphere is happening, no doubt about it. And it's happening at unprecedented rates. And now they're saying that it is extremely likely. Let's see if I can get my pen to work here. Come on, where are you? Extremely likely that human influence has been the dominant cause of observed warming since 1950, and the level of confidence has increased. And they pointed out that the longer we wait to reduce our emissions, the more expensive it's going to become, and things will only get worse the longer that we wait. So there's that. And I start off with this picture of an iceberg. And what we're looking at is bits and pieces, chunks of this iceberg breaking off and falling into the ocean. And it looks almost like an explosion. And an explosion will generate heat. And that is exactly what's happening here. The turbulence of the water generates heat. So what we start out with is an iceberg that has broken away from a glacier or an ice sheet as a result of heat. And now that iceberg itself is generating more heat as it continues to melt. So this is one of those climate feedback mechanisms, and we'll talk more about these, but I want you to just be thinking about it now. And this is a positive feedback where the initial event that occurred, the melting, is now generating more melting. So what is happening here is generating more melting, so it just tends to enhance the heating that occurred to begin with. So when we think of the atmosphere, we think air, but do you ever wonder what the air is composed of? Well, the bulk of air will be nitrogen. Nitrogen composes 78% of our atmosphere. Oxygen comes in next at 21%. See if I can get over here a little bit closer. I have a hard time with this pen. And those two have been in balance with each other for at least 400 million years. And that's good, especially when it relates to oxygen, because if we have around 23-24% of oxygen in the atmosphere, everything would be burning. Even the wettest rainforest would be burning because oxygen is an oxidizer. Conversely, if we have about 19% of oxygen in our atmosphere, we couldn't get anything to burn. We strike a match, it wouldn't burn, not enough oxygen to support it. So those are the two biggies. And then look how the amount drops down here when we get to argon, 0.93%. Argon, it could all be gone. It wouldn't make any difference to us. It wouldn't make any difference to weather. Argon is an inert gas. And you might wonder, okay, how does it get into the atmosphere? Well, as a geologist, this is pretty interesting to me. There are certain rocks that have radioactive potassium in them. Radioactive potassium, potassium 40. And because it's radioactive, that means that it decays. There are nuclear decays. And so we would say this is the unstable parent. And eventually, it will decay into the stable daughter product. And the daughter product is argon. So that's how argon comes to be in our atmosphere. It's from the decay of potassium in rocks into argon. Then what else? Composition of the atmosphere. Again, what else do we have in there? The ones on the preceding slide are considered to be the non-variable amounts. And these next ones are variable. Carbon dioxide, it just keeps rising. We start out in 2005, 370 parts per million, or 0.037%. Then in 2010, it was up to 0.039%, or 390 parts per million, and you will see it just keeps going. In 2015, it was 400 parts per million, 2016, 401, and as of January 2021, 415. So you might think, okay, so what? Well, most reputable scientists think that to keep an Earth like the Earth that humans civilized, we need to be at 350. There's an organization called 350.org. You should check them out. We blew by that with nary a word said by anybody. 350, I see your 350 and raise you 415. So this is very problematic, and we'll figure out why that is, but I'm sure you've probably heard the term greenhouse gas. Well, CO2 is a greenhouse. Other variable constituents in our atmosphere would include water vapor. Water vapor is extremely important because it's what we need for our weather processes to take place. And it varies from 0 to 4% depending on where on Earth you are. That 4% would be around tropical oceans where you have a huge water supply and you have heat to evaporate that water. So most important gas for weather processes, because all our weather is related to water vapor. It doesn't rain sulfuric acid on Earth, it rains water on Earth. Then there are, and I should say that it's a greenhouse gas, but it doesn't stay in the atmosphere for very long, maybe a week at the most. CO2, 100 years. It can stay in the atmosphere for 100 years. Then there are aerosols. These are tiny solid and liquid particles that include things like dust, smoke, ash, pollen, salt. And too much of this stuff is considered to be pollution, but we have to have some of these things in our atmosphere in order for condensation to take place, because water vapor has to have something to condense upon. So these particles provide that. So they're essential, but too much of a good thing can be bad. Then there's ozone. O plus O plus O, three atoms of oxygen combined. And we've got this love-hate relationship going on with this stuff because at ground level, it's pollutant. It makes our eyes sting, it makes us cough, it makes us sneeze, it makes it hard to breathe if you have asthma or an allergy or some sort of respiratory ailment. So we don't like it at ground level, but hey, when it's up in the stratosphere, and it is, the ozone layer up there, crucial to life on Earth because it absorbs ultraviolet C radiation. UVC is ionizing radiation, and you do not want to be exposed to ionizing radiation for any length of time because it does cellular damage, so we can get cancer as a result of it. I'm going to mention climate forcings versus climate feedback here because we just talked about greenhouse gases. And greenhouse gases are important because they absorb heat that is released from the earth. So climate forcings are these influences that cause changes to the Earth's climate system that will alter our radiative equilibrium, meaning changes in the amount of radiation coming in or the amount of radiation going out. And greenhouse gases are one of those climate forcings. So forcing then denotes an external influence on the characteristic of the climate system. Here's another example. Increased emission from the sun would lead to an increase in temperature. Okay, that makes sense. And then feedback is the reaction that the climate system has to that forcing. And the forcing, depending on what it is, can either result in cooling of the earth or can result in warming of the earth. So you might hear this term radiative forcing. Radiative forcing is climate forcing. Radiative forcing, that's the difference between insolation. Insolation is just a fancy word that is short for incoming solar radiation. Make note that it's insolation, not insulation, not the stuff you put, put in your house to keep it warm in the winter and cooler in the summer. So the difference between insolation absorbed by the earth and the energy radiated back to space. These are the radiative forcing components that can have a cooling or a warming impact on Earth. So if we look at these are down here below the zero. This would be those things that would tend to cool the Earth. And then these above the zero line are those things that would tend to warm the earth. So we look at greenhouse gases, and greenhouse gases, because they absorb heat that is released from the earth, their tendency is to warm the atmosphere. So we've got carbon dioxide in here, we have methane in here, we have nitrous oxides, we have some halocarbons. And then tropospheric ozone here would tend to warm the earth. So ozone at the surface would warm the earth, but ozone in the atmosphere, in the stratosphere would tend to cool because it keeps radiation from making it to the surface. Then stratospheric water vapor would warm the earth. Black carbon on snow would tend to warm the earth. Black colors are more absorptive of solar energy, so snow would tend to reflect energy, so that would be cooling, but when we put black carbon on it, it causes warming. Land use changes would be a cooling tendency. Aerosols, these tiny solid and liquid particles in the atmosphere, their tendency is to cool the earth. So if we look at all of those, we find that the overall, if we measure what the amount of warming or cooling is from each of these radiative forcing components, the overall tendency is to warm the earth, even when we take into account those things that cool the earth. So the greenhouse effect then is how the troposphere is heated, caused by the Earth's surface re-radiating long-wave energy into the atmosphere. And it's just this back and forth because the gases that are up there that are absorbing that heat will heat up, they will radiate back, then the heat goes back into the atmosphere, and it's just back and forth, back and forth. Water vapor and carbon dioxide, along with methane and CFCs, are absorbers. Another way to look at it, besides the graph that we just looked at, sunlight coming in, heat going out, re-radiating that heat back to the surface, back and forth. Here's another way, incoming solar radiation, outgoing infrared radiation without the greenhouse effect. Earth's average temperature would be minus 18 degrees Celsius or 0 degrees Fahrenheit. ooh, brr, very cold. But with the greenhouse effect, solar energy comes in, infrared energy is absorbed, and our Earth is this very livable average temperature of 59 degrees Fahrenheit. And that is the temperature that we are concerned about when we talk about the temperature of the Earth warming up. It's that average temperature. Seems slight, but it has major impacts.